Good morning, everyone. I'm TJ, and today I will show you some more geometry idealization commands in NX, and I will teach you some techniques in order to connect meshes from individual solids. I will use a Bowyer-Wilkinson DM602 loudspeaker model, which is prepared by a friend of mine, Magnus Skogsfjord, the NX Portal Oracle, and I will use a three-step approach. First, I will check if it's possible to trim or partition the CAD model to utilize symmetry. Then I will show you some defeaturing commands, pretty much based on synchronous modeling tools, in order to simplify and get rid of pieces and details that I don't want to include in my mesh. I will especially consider the solution I want to run, model analysis. And then at the end, I will check if it's possible to use dimension reduction. That means applying mid-surfaces and shell meshes, if that's feasible or not. First step is to check if I can utilize symmetry in order to simplify my FEM model. In this case, it's not possible because I want to do modal analysis of the loudspeaker, and I'm quite sure that there will be some non-symmetric modes. And if I apply symmetric boundary conditions or apply symmetry, I probably will truncate some modes. So that's not feasible. Here you see my loudspeaker model. And as you can see here, the list of components are quite long. And the first thing I will do is to start removing components of less structural importance. So I start with these rubber inserts. And then the bolts, like this, delete. The next thing I will do is to remove my base port. It is a plastic, thin plastic. The mass is probably like 100 grams, so it's not really important. But I will represent it with an RB3 element with a center node with an additional mass of roughly 100 grams. Then the base element, it has some structural stiffness, but I don't know the details, so I choose to simply remove it. And my idea is to represent it with an RB3 or RB2 element with a center mass representing the base element mass. Then the tweeter, same here, it's a plastic part, and I select the rigid bodies or the bodies, and here I think I'll have a couple of sheet bodies. Let's get rid of those like this. Then I have a logo, which I think is represented by solid bodies, so I want to get rid of them as well. There. And on the rear side there is a plastic bracket with connectors, loudspeaker connectors, and I choose to remove them as well. And I will also represent them with an RB3 element, which connects the edges here. And in the center I will apply a dummy mass representing the mass of the connectors. So now you can see my component list here has shortened dramatically. And I'm ready to start using synchronous modeling commands in order to remove unwanted features. The first features I want to remove are the chamfers or blends. So I'll use the delete face command, and I use the selection filter connected blend faces, and I will choose these, and I will apply to remove them like this. There are lots of them, so let's be careful that we remove them all, because these will pretty much ruin my mesh. Apply. Let's see, here are some more. That one. Here's a couple as well. Apply. And there's another one. I could also use delete faces in order to get rid of this pattern. But here are probably thousands of these small features, and it will take some time to remove and replace faces on all these small features. So I will instead do something else. I will go to the replace face first, and then I will replace this face with the center wall of the loudspeaker, like this. That one. This takes some time. You see, if I merge these models, there will be a very thin surface left here, which will pretty much ruin my mesh as well. Takes some time to replace all these faces. And that one. There we go. Apply. And now it's time for a save. My next task is to get rid of this feature pattern on top. You can see here are hundreds or perhaps thousands of these small features, and I want to get rid of them. I could have used the replace face like this. I could have chosen this face, and I could have replaced it with this face. That's one option. But that takes quite a lot of time. I could also use delete face on each of these. The best option would be if I had the history tree to use to delete the command that generated all these small or this pattern. In this case, I will do something else. I will use an extrude command, and I will use it to slice off the front pattern here on this loudspeaker. So I select the surrounding edges. Make sure I'm selecting the right edges. Let's zoom a bit there. And if I go to none in the Boolean, you can see that I'm getting a solid part. Then I don't want to remove the front plate or more than the pattern. So I think the thickness of the pattern was 0.2 millimeters. And now I can select subtract, and I want to subtract this extrude from the front plate. And I press apply. And this will take some time. There we are. You can see that the extrude command slide off the front pattern. You see it's a little bit thinner, but that's okay. And now I do the same with the other front pattern. Like this, and I subtract from this one. Apply. There we are. Now you can see that I've sliced off the pattern completely, and I got a clean front, which is simple to mesh. I've also removed all fillets, but no, I have actually not. So we have to clean a bit here, delete face, and I use connected blend faces because I have blends in the lower part of my plate. You can see there. Press apply, and I think it's the same with this one. These small features will completely ruin my mesh. Then I see something else. There is a distance between the two front plates, and that's probably not the intention. I don't know why it's modeled, but I will now use replace face, and I select this face, and I want to replace it with that face. And now you see there is no gap anymore. However, these two models, solid parts, they are not connected, or these three parts. I will show you how to connect these so that the mesh is representing one solid part and not three different disconnected meshes. However, I also will consider to remove some features here, like the holes. I don't think they will represent any major stiffness contribution or removed stiffness. So in order to make a clean mesh here and make the loudspeaker easy to work with, I just delete these faces. Not connected blend faces, I have to use single face like this. Apply. Apply. Of course, you could argue whether to keep these holes or not. But in my situation, I don't have the details inside the loudspeaker either, so I don't care to keep them. And also with this feature, I think I will just replace this face with the front face like this. So this is a really clean loudspeaker. And for loudspeaker optimization, which is the next exercise in this course, this is a good start point. Now I can easily add ribs and change the thickness of plates, and it's easy to update the mesh and check the consequences of the changes I've made. And as you know, the point with the objective with this exercise is to prepare a loudspeaker for model analysis. So small features are not of great importance. I'm not looking for stresses or strains in local areas. What I want to do is to optimize this loudspeaker so it has no resonance frequencies in a selected bandwidth represented by your favorite instrument. In the video tutorial, I'll show you how you can optimize this loudspeaker for power chords to avoid resonances. Then I have defeatured my solid model, and the next task or question is if I can reduce the dimension of the loudspeaker. That means replace the solid geometry with a 2D geometry. And here I could easily use mid-surfacing in order to create a shell mesh for the loudspeaker. That would give me a faster solution when I do model analysis. And it would also be beneficial if I wanted to change the thickness of the plates. Then I could just simply change the thickness of the elements in the collector. However, I might need to redesign the loudspeaker with inner ribs and stiffeners and other things. And then it's easier to keep a solid geometry in the design process. So in this case, I don't want to do it because these walls are rather thick. And as I said, it's easier to edit the solid geometry. So I will keep my model like this. And now we will have a look at how to mesh this loudspeaker and connect the meshes. So my model is defeatured. But if I use selection filter solid body, I see that I have many solid bodies still here. You see here from the list. So the first thing I want to do is to unite the side panels here and the rear side as well. Then I have 3 solid bodies. I have the 2 front panels and the loudspeaker cabinet. I might also change or replace this edge here. I could use replace face on that one too, but I keep it like this. So I have 3 solid bodies, and there are 3 different ways to connect the meshes, because I don't want 3 independent meshes, because that would give me 18 rigid body modes in the model analysis, and I only want 6, because then I know that my mesh is connected. The easiest way is, of course, just to unite these like this. Then you see there is just 1 solid body left, and if I mesh it, the mesh will be connected. But we could imagine that these 2 panels and the cabinet has different material properties, so I don't want to do it. So what are the other options? First, let's create. I have to go to application, pre and post. And then I want to create a new FEM and simulation. I don't want to create an idealized part because I didn't use best practice. I idealized my original master geometry, while I should have idealized the idealized part, of course. But that's not so important right now. And here I choose 103, SOL 103, real eigenvalues. And let's change the eigenvalue settings, the Lanczos data. I need more than 10 modes. I will select 20 modes. Okay. I keep all other default values. So here's my FEM file, and the next task is to mesh it. First, I want to make some material data. I go to library materials, and I don't have wood. Wood is an anisotropic material, but for this demo, I just choose another simple material like polyethylene, if I have it here. There it is. And I right click and I copy it. And I call it fake wood. And then I use an E modulus. I could use 1000. Poisson ratio 0.4. I keep just the density like it is. And I press OK. Then I have the fake wood material. And then I'm ready to mesh. I can mesh these 3 parts. I use the lightning symbol to estimate a proper size, and I reduce it a bit, 20 millimeters, and press OK. Okay, there you see my mesh. Then I have to make sure that my mesh has the right properties, and I go to solid 1 here. I edit the solid properties, and here I can't use inherit because I haven't applied material properties to my geometry, so I have to select fake wood like this, and I can name the collector fake wood. There we are. Now I have 3 different meshes, as you see here. These are my 3 meshes. And one check to verify if these meshes are connected is to use duplicate nodes. And for example here I have 2 common faces, and you see here are duplicate nodes. And if I applied or pressed merge nodes, those nodes will disappear and the mesh will be connected. However, you are never guaranteed that these nodes are exactly positioned, and there is a tolerance here. And if the nodes have a distance which is longer than the tolerance, you would still have disconnected edges. So this is not the method I want to apply, but I want to show you what happens if I run the simulation with this mesh. First, I make work part on my sim file, and I can run the solution to check the results now. I choose my solution and I press solve. And as you remember, I requested not 10 modes, which is the default choice. I requested 20 modes. And you soon will see why. Then my simulation is completed and I can check the results. And here you see my list of my modes. And what you can notice is that my first 6 modes has an eigenfrequency of almost 0. And the same with the next 6. And even mode number 18 has a almost 0 Hertz eigenfrequency. And if I animate these, or let's say select mode number 1, you can see that this is a rigid body mode. I can step through the modes, and you can see that these are all rigid body modes. I added no constraints, so all these parts are free to move in 3 directions and rotate about 3 axes. So all these are rigid body modes until I come to mode number 19. Here you see that this mode includes material strain, and it deforms the structure, and you can see that the eigenfrequency is 25 Hertz almost. But here you see what happens if I apply no constraints and I have no connections between my meshes. Then I will apply a technique in order to connect the meshes, my first option. Then I make my FEM model, the work part, and I use this command, mesh mating. And I choose all solid bodies, and I use this option, glue coincident. And I press OK. Then you don't see anything, but I need to update my part. You see this small arrow here. I can press on this update button. I know you can check if I have coincident nodes or duplicate nodes. There are no duplicate nodes. If I list them, there are 0 duplicate nodes. And that's good. And then I can run the simulation once more. First I have to activate my sim file, make work part, and I run the simulation. Solve. OK. Then my new run has completed, and I can check the results once more. Let's see. First, I have 6 rigid body modes. Let's have a look at those. I select displacement, and here I can of course animate them. This is my first, my second, my third, and I can display all my 6 modes, and as you see, they are rigid body modes. There are no structural deformation until I come to the 7th mode. And then you see a mode which is exactly 85 Hertz. And this is a valid mode. I could have applied constraints on the bottom of the loudspeaker, but you know, you don't glue your loudspeaker to your shelf. So I don't do it. So this 85 Hertz, if you're a guitar player and you play power chords, you know that the lower E string has this frequency. And if you play power chords on this loudspeaker as it is, it might start to vibrate. However, I haven't applied the RB2s and RB3s, which represents my elements. So far I've just shown that I can use mesh mating to connect the meshes. Let's explore a third option. As you noticed, mesh mating works fine on solid geometry. However, there is a third option. My sim file is now my active part, And what I could do instead of using mesh mating, I could go to simulation object, and I could create a new simulation object, and I could use surface to surface gluing. And I could select all my solid bodies. That would have the same effect. However, it wouldn't actually merge the nodes. What happens then is that NX is using an augmented Lagrange method in order to connect the degrees of freedom or the equations during solution. So it might take some more time, but this option is really nice if you want to glue together elements of different types. So this is a good practice. However, it only works if you select NX Nastran as your solver preference. If you want to connect your meshes and export it to another solver, this technique wouldn't help you. Then you have to use mesh mating. So right now I just keep my mesh mating conditions, and I will show you how to represent the loudspeaker elements. So let's add some RB3s. First I want to make my FEM part, my working part, and then I can use 1D connections. First I want to model my base port, and then I choose 1D connection point to face, and I can click on the edge here, and then I get the center point, and I click on this face. And in this situation I choose to use RB3, and an RB3 element is a soft connection. It doesn't, the surrounding nodes are masters and the center node is a slave. And that enabled my porthole here to deform. It doesn't enforce a rigid, stiff connection like the RB2 element. And I press apply. That's okay. And then I do the same with the loudspeaker element. I selected my center node and the surrounding faces. And here's a question if I should use RB3 or an RB2 element. In this example I choose RB2 because I imagine that the loudspeaker element is very stiff. And if I use RB2, this will be an infinite stiff connection, like this. And then I have my tweeter, and I use the same technique, but here I think I'll use RB3 again. Then we can see how the different techniques work. And to select a point, I don't have a center point here, so I choose the dialog here, and I select between 2 points. And I select 2 diagonal points here. Then I will have the center point. And then I can select the surrounding faces. And here I choose to use RB2 because I imagine that the tweeter is not very stiff. And it's the same with the rear side here. I use the same dialog. I use between 2 points. Select this point and that point. OK. And the surrounding edges here. Of course, this is not really a detailed way of doing it. I just show you the principles here. And I press apply. Then I've sort of represented the stiffness of the elements. I could have done it more exact, but I don't have the properties of the elements. Another thing I want to do is to use, I go to more, and I want to apply a 0D mesh. Here I want to use a COM2 element, and I select the center node here. And I press edit mesh associated data. And here I want to apply a lumped mass representing the loudspeaker. And I honestly don't have a clue, but let's imagine that the element weighs 2 kilos. I press OK, apply. And then I've added 2 kilos in the center here. The next thing I do is to apply a mass representing the tweeter. And I use the COM2 element. And let's imagine that the tweeter is 0.2 kilos, perhaps. That's not much, 0.3 perhaps. And I press OK. What you should know is that this node where I applied the mass is a slave node, because in an RB3 connection, the surrounding nodes are the masters, and that means that these degrees of freedom, they will disappear during equation solution. And the mass, which I applied here, will be distributed around the surfaces are here. Then I'll do the same with the base port. I use a column 2 as well. Let's imagine it weighs 0.1 kilo. Apply. Then I could, of course, add some mass representing this connector at the rear side. 0.1 perhaps. There we are. This will probably influence the results. And let's run the simulation once more. I go to my sim file, make work part, and I press solve. Okay. There we are. The solution has completed, and let's now check the effect of the RB2 elements. I can see that my first 6 rigid body modes are here still, but I want to check out mode number 7. And you see that the frequency has reduced from 85 to 81 Hertz, which is probably due to the added mass I put on here. And you can also see from the mode shapes that the displacements are concentrated around the side panels. So that's why my RB2 here didn't influence too much on the displacements and the mode shape. But you can tell from the animation that this hole hasn't deformed. It's a rigid connection, so it won't. While this one, which is representing the tweeter, here you see that the edges are bending because I'm using an RB3 element. So that pretty much conclude my presentation about loudspeaker idealization and meshing.